So average turnaround time will be for process P, for process Q, plus for process K, and all the processes upon N. N is the total number of processes. So for process 1, process 2, up to process N upon total number of processes. So in total, CPU utilization should be high or low. Yes, it should be high. Throughput should be high or low. It should be high. Average response time should be high or low. For better operating system, average response time should be low. For total average waiting time should be high or low. It should be low. Average turnaround time should be high or low. It should be low. So if these are the criterias, and and if they are like in such a manner so that CPU and throughput CPU utilization and throughput are high, and average response time, average waiting time, and average turnaround time are low, then our operating system is better. So all the operating system work upon these criterias, and they have a competition in the market. So you see that the operating system which people use in Mac, the operating system which people use in Windows, the operating system which people use in Windows mobile phone, the operating system which people use in Android mobile phone. So there is a heavy competition just on the basis of this operating system. And operating system, the developers work upon these 5 criterias and try to improve their operating system so that the market can be on their favor. So coming next to the scheduling algorithms. So the first one is first come first serve. First come first serve. Suppose there are processes P1, process P2, process P3, and burst time is 742 burst time, that is CPU burst time, and arrival time for these processes are 0, 2, and 3. So if we draw the Gantt chart for this this specific scenario, so it will be like first come first serve, whichever process has come first, yeah, serve it completely, and then when it finishes, then only another process can enter. So here we could see that process P1 has come at 0 time, so process P1 takes the CPU burst up to 7 milliseconds, and process till that time 7 milliseconds we could see that process P2 has come into the ready queue at time 2 milliseconds, and process 3 has come into the ready queue at 3 milliseconds. So operating systems take into consideration that process P2 has come first, then process P3, so allocate CPU to process P2. So we could see that as soon as process P1 finishes, first come first serve. So first come who came first among P2 and P3? P2 has come first. So P2 is allotted the CPU, and then P3 has allotted the CPU. So we could find out that CPU percentage utilization is 100%. Total time it is from 0 to 13, and 100% the CPU is not sitting idle for any time. It is fully utilized. Now computing the second parameters, that is average response time, it comes out to be for process P1. Let us see for process P1 it came at time 0 and it got the CPU at time 0. So it need not wait for any amount of time. So it is 0 plus for process P2 it came at time 2 millisecond and it got the CPU at 7 milliseconds. So it is waiting time is 7 minus 2, and for process P3 it came at 3 millisecond and it got the CPU at 11 millisecond. So 11 minus 3 upon total number of processes. Total number of processes are 3. So it is 13 upon 3. Next criteria is average turnaround time. First let us see here what is the average waiting time. Average waiting time is the total time for which a process has to wait in the ready queue. So here we could see the process is waiting only for this much time only. Process P1 has to wait for nothing. Process P2 has to wait for, it came at time 2 and it got the CPU at time 7, so 7 minus 2. Process P3 came at time 3 and it got the CPU at time 11, so 11 minus 3, and it is waiting only for this much time. There are no for no other durations any process has to wait in the ready queue. So it is same as average response time in this particular case. Now computing another criteria, that is average turnaround time. So it is the start time of process, like it is the finish time of process P1, that is it is getting over at 7 millisecond, and the time at which it came in the ready queue, that is 0 millisecond, so it is 7 minus 0, plus the time process P2 came to the ready queue, uh, the time at which process P2 finished, that is at 11 millisecond, and the time when it came to the ready queue, that is it came at 2 milliseconds, so it is 11 minus 2. Process P3, it is getting over at 13 millisecond and it came to the ready queue at what time? At 3 milliseconds, so 13 minus 3 upon total number of processes are 3, that is 8.67, and throughput is total number of processes executed per unit time. So total number of processes are how many? 3, P1, P2 and P3. So 3 upon total time is 13, so 3 upon 13. So it is a very simple example. So what are the advantages of first come first serve? It is very simple to implement. We can see whoever comes first, but yeah, allot the CPU to that particular person and don't disturb him until he have a good interaction with CPU. After that only any other person can come and meet CPU. Another advantage is that no starvation. No starvation. How? Because whoever comes first, he will have he will have a wonderful interaction with the CPU and nobody will disturb him. No other process will preempt him till his discussion has been completed with the CPU. So whoever comes, he will get the CPU definitely, provided each process is of finite time, of finite CPU burst time, then nobody will be starving. Suppose if we consider last come first serve case. Considering last come first serve case, what will happen? Whoever comes at last is served first. So suppose new processes are arising, coming, old process will not get any CPU, because whoever is coming at last, he is getting the CPU, and new process more and more are coming. So whichever process has come for the first time, he is not getting the CPU, so he may starve. So moving ahead, this example you can practice by yourself, or I will give you an overview. Suppose there are processes P1, P2 and P3, and P1 is having a CPU burst of 7 millisecond, then an input output burst of 10 millisecond, then a CPU burst of 3 millisecond, and it arrives at 0 milliseconds. And similarly, process P2 has a sequence of CPU burst, input output burst, and CPU burst of 4 millisecond, 12, 20 millisecond, and 5 milliseconds, and it arrives at 2 millisecond. And similarly, process P3 have CPU input output and CPU burst as follows, that is 2, 25, and 6, and has an arrival time of 3 millisecond. So now you need to draw a Gantt chart for this particular scenario, considering that input output operation for process P1, if suppose P1 is going to input output device 1, process P2 is going to input output device 2, process P3 is going to input output device 3, then they can do it in a parallel fashion. So considering that particular assumption, we have to draw the Gantt chart. So P1, we can see here it has come at 0 millisecond, it came here at 0 millisecond, and it is going through a CPU burst of 7 milliseconds. So for 7 millisecond it has come. Next, it is going to perform an input output operation for 10 millisecond. So input output burst for 10 millisecond up to 17 millisecond. So we can see that at time 2 millisecond, process P2 has already come in the ready queue, and at time 3 millisecond, process P3 has come. So first come first serve, that is we will give priority to the process P2. Now it has to perform its CPU burst for 4 millisecond. So from 7 to 11, that is it goes through its CPU burst, and thereafter we can see that process P3 is waiting in the ready queue because it has already come at 3 millisecond. So it performs a CPU burst of 2 millisecond. So it goes and performs from 11 to 13 millisecond. And the time being, process P2 has gone to perform its input output operation for 20 millisecond, that is from 11 to 31. Now we could see that there is no process which is available, as at time 13 millisecond process P3 also goes to perform its input output operation for 25 millisecond. So we can say that we can see that here process P3 up to from 13 to 38 millisecond it has gone to perform the input output operation. So here all the processes, P1 is going through an input output burst, P2 is going through an input output burst, P3 is going through an input output burst. So none of the three processes are idle, are free for having an interaction with CPU. So CPU is sitting idle here. As soon as process P1 is completes its input output burst, it goes to the CPU and perform a 3 millisecond of CPU burst up to 20, and then again we can see that P1 process has finished, but still neither P2 is free nor P3 is free. So as P2 becomes free, it completes its CPU burst of 5 millisecond from 31 to 36 and gets finished. And again here the CPU has to sit idle because process P3 is going through its input output operation, and at 38 millisecond whenever it finishes, it goes to the CPU burst and gets completed. So now similarly we can compute its CPU burst, that is CPU utilization percentage. It is from 0 to 13, uh, 0 to 13, 17 to 20, 31 to 36, 38 to 44. So it comes out to be 27 upon total is from 0 to 44 milliseconds, that is 27 upon 44. So this is a CPU percentage utilization. If we compute the average response time, so it is how much? For process P1, it is the first time for which a process has to wait in the ready queue. Process P1 has to wait in the ready queue for how much time? For the first time, 0 time, because its arrival time was 0, and it has, as soon as it came, it got the CPU. So 0. Process P2 arrival time was 2 millisecond and it got the CPU at 7 millisecond. So 7 minus 2. Process P3 arrival time was 3 millisecond and it got the CPU at 11 millisecond. that is 11 minus 3. So this upon total number of processes are 3, so this is the average response time. Now what is the average waiting time? Average waiting time is the total waiting time in the ready queue. So for process P, for the first time it has to wait, we have already computed 0, 7 minus 2, 11 minus 3. But again, considering that for the first time it has to wait for 0 millisecond process P1, for the second time we can see here, as soon as the process P1 completes its input output operation, it gets the CPU burst, so it has to wait again for the 0 time. Then considering for process P2, first time it has to wait for, like, it came for 2 millisecond and it got the CPU at 7 millisecond. So for first time it has to wait for 7 minus 2 millisecond, and again as soon as process P2 completes its input output operation, input output burst, it gets the CPU, so it has to wait again for the 0 time. And then for process P3 we could see that for first time it has to wait, it came at 3 millisecond and it got the CPU at 11 millisecond, so 11 minus 3. And for the second time, as soon as it completes its input output operation, it gets the CPU, that is, it has to wait for 0 millisecond. So average waiting time is this upon 3. And throughput is how much? Total number of processes are 3 and total time is from 0 to 44, that is 44 milliseconds. So it comes out to be 3 upon 44. And average turnaround time is, it is a time when the process is finished and the time for which it has come to the ready queue, that is, it is for process P1 it has come at 0 millisecond and it is getting done with at 20 milliseconds, so it is 20 minus 0. For process P2 it is getting done at 36 millisecond and it has come at 2 milliseconds, so it is 36 minus 2. And for process P3 it has come at 3 millisecond and it is getting done at 44 milliseconds, so it is 44 minus 3. So 44 minus 3 upon 3. So this is average turnaround time. So very simple. You can practice more such examples to have more clear understanding of the criterias, how to compute which one is better, which one is not good. So coming to our next algorithm, it is shortest job first or shortest remaining time first. So it could be a primitive or non-primitive. Primitive means higher priority process can preempt a lower priority process, or a timer interrupt can also preempt. And non-preemptive means a process P either go for the input output operation or it's terminated. So let us see an example and get the things more clear. So considering this example, this is the CPU burst time, arrival time, the processes. Considering the non-preemptive approach, that is, no process can preempt. Once the process has come in the cabin of the CPU, no other process can know and disrupt that particular process. So this is non-preemptive, no disturbances. So here we could see that process P1 has come, arrival time is 0 millisecond and the CPU burst time is 7 millisecond. So it is going, the CPU burst is from 0 to 7. Then in the meantime, process P2 and P3 both are waiting in the ready queue. So P2 has come first, so bhaiya, no, we will evaluate here. See, process P1 has come at 0 millisecond and no other process is present in the ready queue. So we have no other option. Just give the CPU to the process P1. And it is non-preemptive, then even if other process come in this particular time, they cannot take P1 out. P1 has to complete, and then only P2 and a decision could be taken between which process to be sent to CPU, either P2 or P3. So whenever P1 finishes its CPU burst time, we we make a decision, because now two processes P2 and process P3, these two processes are waiting in the ready queue. So we make a decision depending upon the CPU burst time. For process P2 it is 4, for process P3 it is 2. So I am a bit confused out here. This example I need to check that once the process P1 has completed, then which one should come, P2 or P3? This this I will clear you out whether P2 should be executed or P3 should be executed. I have a doubt here, because we should make a decision depending upon the, I will let you know just in next lecture. So considering the primitive case, we could see that process P1 has come. So it has come at 0 millisecond arrival time. So here we can see that it is a 0 millisecond. So we can see here that process P2 has come at 2 milliseconds. So it has come at 2 milliseconds. So process P1 has to execute from 0 to 2. Now it has executed for 2 milliseconds, that is still for 5 millisecond still CPU burst has left. So now we have to make a decision between, at 2 millisecond two processes are present in the ready queue. One is process P1 and one is process P2. So whichever is shortest, process P2 is shortest, so process P2 is given the CPU burst. And we can see that at time 3 millisecond process P3 has come. So it will execute only for 1 millisecond, and then again a decision has to be made between which process to be given the CPU burst, that is P1, P2 or P3. So we can see shortest job is for P3. So P3 is given for 2 millisecond, it has been completed from 3 to 5, and then we will see among P1 and P2, P2 needs to be given. So P2 is given for 3 millisecond between 5 to 8, and then only process left is P1, that is for 5 millisecond. So what is the disadvantage of this particular algorithm? So the disadvantage is context switch time, context switch overhead is increased. We could see out here that the switching between the processes has increased, so overhead of context switch is increased. So in case there is a tie, if suppose two processes P1 and P2 are having a same amount of CPU burst and they are waiting in the ready queue, so how will break that tie? On the basis of first come first serve. Whoever comes first, he is given the CPU first, and that's it. So its advantages are its throughput is high in case of processes continuously arriving, and it has least average waiting time. By intuitively we can see these things. The advantage is that a priori estimation of next CPU burst is very difficult. So that's why this algorithm is theoretical algorithm. It cannot be implemented in operating system, and starvation is possible. Suppose shortest job first, like who, if the new processes keep on coming, who's having the shortest job? the longer programs will never get an opportunity to have a discussion with the CPU. So they will be waiting for long and long time. So starvation is possible. So this algorithm is not used in operating system. If it is being used, then what will happen? Operating system ki tabhi. Whoever has developed this operating system, the company will sue him. He will be trouble for the company because the market will not be in favor of this particular operating system, because all processes run ही नहीं करेंगे. Some are getting their the opportunity to get run, another will not get CPU burst. They'll be waiting for endlessly still. So some processes are, that's why round robin algorithm has a key role. Even most of the uh, operating systems in present scenario are using the variants of round robin algorithm. So how it works? Suppose we are in a railway station. Here is the counter, and suppose these are the persons: person A, person B, person C, waiting in a line to get their railway ticket. And suppose a person has brought 50 forms with him. Person B has brought 2 forms. Person C has brought 1 form. So what will happen? If person A is given an opportunity कि भैया you have done, you get your tickets done for 50 forms, then persons B and C, so they will become bewildered. What is this? We have come and for 2 hours you are booking the tickets for person A only. So what they have designed, that we will give a time quanta that at a time each person can have 2 forms only, that you can book tickets for 2 forms only. So person A will book tickets for 2 forms, then again he will go back and stand in the line with its remaining 48 forms, and we will get an opportunity. So we have given a time quanta here of 2 forms, that is each person can book tickets for only 2 forms. So advantages here is that, what are the advantage of this particular algorithm? It is a fair algorithm. How come it is a fair? Because a person who is having more number of forms, a person who is having a process who is having a high amount of CPU burst, then he has to wait for the longer time. And the person who is having less forms, or the process who is very short, he has to wait for a shorter time. So it guarantees upper limit to response time. And if a process wants CPU burst time greater than TQ, it will have to go in the ready queue for the multiple times. So advantage is it has good user interactivity. Good user interactivity means if the user wants to have a new processes initiated and wants to have some kind of a feedback, then it will get the CPU. CPU will not, in case of first come first serve, bhaiya, till the process is not executed completely, CPU will not be entertaining any other process. But there are so many processes that user needs to have an interaction with the CPU in between a hand. So in that case, in a round robin fashion, each process will get a chance to have an interaction with the CPU. So it is easy to implement and it is fair. So disadvantages are more amount of context switches, because after that specific time quanta, say 2 milliseconds, each process P1 will be using a CPU burst for 2 milliseconds, if we have kept time quanta to be 2 milliseconds, then again there will be a context switch. Suppose total CPU burst time was 15 millisecond, then again process Q will come to the CPU. It has its total CPU burst was 4 millisecond, and then suppose process R CPU burst was 2 millisecond. So if time quanta is 2 millisecond, first come first serve case, how many context switches will be there? From P to Q and Q to R, only two context switch. But in case of round robin, after every 2 millisecond there will be a context switch. Then its remaining time will be 13, and it will be a context switch to process Q. Then its remaining time will be 2. Then there will be a context switch to process R. Then its remaining time will be 0. Then there will be a context switch to process P. Then the remaining time will be 11. Then context switch to process Q, remaining 0. Then this. So there will be n number of context switches in comparison to first come first serve or spotted job first. So yes, there is a difficulty to estimate a good value of TQ. Suppose uh, considering the extreme cases, if TQ is equal to context switch time, then your efficiency CPU utilization will reduce to 50%. So these are the disadvantages. So this is the end for today's lecture, and yes, we will be meeting in the next lecture. Hope you will study. Thank you.